Okay, good afternoon, everybody. Here we go. Just before we start diving straight into the lecture, a couple of things to mention. This is the last lecture. I will get this recording up hopefully tomorrow, so that those of you who need to go over it again will have time before hitting Thursday. What's happening after this point, of course, is we've got 3 more classes available. We have Thursday the 20th. We have Tuesday the 25th. And we have Thursday, the 27th. And all 3 days are test days. If you still have tests that you need to take and you're not sure whether you're going to be quite ready for this Thursday, that's fine. There are 2 other days after that. If you have 3 tests left to take, then obviously you'll be taking tests on all 3 days. The other thing is, it is also question day. So, if you're working through things and you know that you've got some time, but you've got some problems with stuff that you still want questions on, I will be holding a room, much like we've been doing on all of these other test days, where people can be in there and I will work problems with you. So if you know that you've got things that you would like to work through or questions that you would really like me to do in detail with you, you can make sure to show up for those things, even if you're not taking a test, and I will happily work questions with you. Any questions on that stuff just before we go? Because once I start into the lecture, I'm going to forget to talk about these days. If you don't have any questions on that, that's fantastic. I'm looking forward to seeing you on the Thursday, Tuesday, and Thursday. Oh, and just one more thing to be clear. If you've taken your final test on Thursday and you're not planning on retaking any tests, you do not have to show up for the other days. You only have to show up if you're taking tests or have questions. Okay, with all of that, let's jump into today's lecture and get started. Solving equations. This is something we've been doing a little bit of informally as we've been working through the course in various ways. Anytime you come up with an answer to something, not just sort of simplifying an expression, but when you actually get down to x equals some number, then you have a solution. And that's essentially what we're going to do. Now, in solving equations, one of the things that's incredibly useful is this very important fact. If you have 2 numbers, we'll call them a and b, and you multiply those 2 numbers together and your answer is 0, then you know for certain that either a is equal to 0 or b is equal to 0, because 0 times anything gets you back to 0. Or it's quite possible that both are 0. That is yet another option. And we're going to use this fact in some factored expressions. So if we factor an expression, you've been possibly wondering, why would we need to take these things apart? What's useful about taking apart all of these expressions? If we factor an expression into individual pieces, we can check what happens if those individual pieces are equal to 0, and that allows us then to come up with solutions to these equations. So, for example, if we're given x to the 5th times x minus 3 times x squared plus 3 times x squared minus 7, and we set the whole thing equal to 0, there's a bunch of stuff we can automatically know. We know that one of these things, or potentially all of these things, are equal to 0. So we work through each of the terms and see what it tells us. Well, if x to the 5th is equal to 0, and I'll just throw a little quick if out front of there. If x to the 5th is equal to 0, then we know that x must be equal to 0, because the 5th root of 0 is still 0. If x minus 3 is equal to 0, then a quick bit of algebra lets us know that x must be equal to 3. Easy enough. If we take a look at the x squared plus 3 expression and we set that equal to 0, that implies then that x squared is equal to negative 3, which then implies that x is equal to the square root of negative 3, which we cannot do. We cannot take the square root of a negative number, so there is no real solution there. If, however, our x squared minus 7 term is equal to 0, this implies that x squared is equal to 7, and that implies that x is equal to plus or minus the square root of 7. So now we have a bunch of actual and real solutions. X equal to 0, x equal to negative 3, x equal to plus or minus the square root of 7. So then we can say that the answers are, the solutions are x equal to 0, or x equal to 3, or x equal to the square root of 7, or x equal to the negative of the square root of 7. Any and all of those answers are correct. When we're trying to find answers to polynomials, the very first thing we want to do each and every time is factored. In our very first example, it was given to us factored, which makes life easy. Most of the time, though, it won't necessarily be given to you in factored form. In fact, it won't necessarily be given to you in a nice, straightforward form at all. You need to get it back to some sort of familiar form. We'll start with an example where we just need to factor. If we are given x squared minus 5x plus 6 equal to 0, we can go ahead and factor this. What multiplies to make positive 6 but adds to make negative 5? And our answers end up being negative 2 and negative 3. So we set those things equal to 0, which means that each individual part we can set to 0. So x minus 2 equals 0, or x minus 3 equals 0. A quick moment of algebra tells us that x equals 2, or x equals 3. And those are our solutions. Now you might be wondering, and it's a perfectly easy thing to wonder, what happens? Why do we end up with two answers? And one of the things that I wanted to do is I wanted to show you what this ends up looking like when we graph it, just so that you have an idea of why there are two things equal to 0. So that's what I'm going to do with the next example. We'll start off by being given this big, large thing, 3x squared plus 17x plus 75 equal to 2x squared plus 5. Well, this is not anything we're familiar with. We don't have any references for graphing that, and we don't yet have any references for solving a thing like this, so we're going to rearrange it. Step 1, rearrange. And in this case, rearranging it basically means put all of your terms onto one side of the equation. So we start off with 3x squared plus 17x plus 75 equals 2x squared plus 5. Well, what we want to do is we want to move the 2x squared to the other side, so we're going to subtract it from this side. If we subtract it here, we can subtract it here. At the same time, we can do the 5. We subtract it from this side, which means we subtract it from this side. And when we do that, we end up with 1x squared, 17x comes down on its own, and then 17 minus 5 gives us 12. Sorry, that's not a 17. That's a 75. I thought that looked funny. There we go. 70. Much better. 2x squared minus 2x squared is 0. 5 minus 5 is 0. So this side is now equal to 0. Well, this is much easier. We're used to dealing with this. We know how to factor these. We're going to ask ourselves what multiplies to make 70 but adds to make 17. we work our way through our times table, and we discover that the answers are going to be 7 and 10. So this then factors into x plus 7, x plus 10 equals 0. From there, we can, so I should have stopped at this point and said step 2. Factor. That's been done. Step 3, solve. So this is where we say x plus 7 equals 0, or x plus 10 equals 0, which means x equals negative 7 or x equals negative 10. And those are our solutions. Now, what does this all look like if you graph it? Going back to our wonderful calculator, the Desmos calculator. Y negative. Good question. So the reason it's negative, if x plus 7 equals 0, then x needs to be negative 7. Negative 7 plus 7 equals 0. So they have to be the opposites of each other. Okay, this was the equation we started off with. This 3x squared plus 17x plus 75 minus 2x squared plus 5, that funny looking thing. And if we show the graph of that, I'm just going to scooch over here, we don't actually get to see too much of the shape of the whole thing, but we can see where it crosses the x-axis. And if we zoom in on it here, we can see that we cross at the points negative 10 and negative 7. So those are our 0 points. When our y is equal to 0, our x is equal to negative 7 and negative 10. So that's what happens. Now, when we rearrange this whole equation so that it's much simpler, well, you can see that now the graph is much simpler. It's something we can actually start to see the shape of, but nothing's actually changed. It still passes through those same 2 points. So the solutions, as we're looking for them, remain the same at negative 10 and negative 7. I think I threw in the first one that we did here, the x squared minus 5x plus 6 equation is also here if you wanted to take a quick look at it. We knew what our solutions were for that. We knew that they needed to be 2 and 3, and when we take a look at the equation, there they are. We passed the point 2 and we passed the point 3. Okay, so moving on to our next example. And I will be coming back to this for a number of these graphs. I'm just going to do a couple of work problems, then we'll go back and examine them on the Desmos calculator again. So, moving on to the next worked example. We are given 3x squared plus 13x equals 10. Step 1, we rearrange. We end up with 3x squared plus 13x minus 10 equals 0. We do some AC factoring. So a quick reminder for those of you who have not been quite as comfortable with that, AC factoring is when we multiply our first and our last term together. In this case, it gets us negative 30. We're looking for the terms of negative 30 that are going to add to give us positive 13. And in this case, those terms are going to be positive 15 and negative 2. This now allows us to move on to step 2. We're going to factor. So taking those terms, that tells me that 3x squared plus 15x minus 2x minus 10 equals 0. Out of these two terms, I can factor out a 3x, which leaves me with x plus 5. Out of these two terms, I can factor out a negative 2, which again leaves me x plus 5. Solving this then, I have a term x plus 5, my other term 3x minus 2. This means now I can move on to step 3, solve. X plus 5 equals 0, or 3x minus 2 equals 0. This one is straightforward, x equals negative 5. This one takes a little bit more. It lets us know that 3x is equal to 2, which means that x is actually equal to 2/3. And those are our solutions. Okay, before I go too much farther, let's just check in really quickly. Is everybody still with me? Okay, most of us are okay. Great, thank you. Okay, one of the things I want to mention at this point, and I put it in the notes, it's important that we solve by factoring. Don't lose any of your pieces as we go through here, because if we divide them out, we might lose some of the solutions, and I'll show you what I mean by that. So, moving on to the next worked example. We're being asked to solve x to the 6th minus 16x squared equals 0. Now the nice thing about this, it's already been rearranged. Step 1 is already done for us. We're fine, so we can just go ahead and start factoring all of this. The first thing that we notice that we can factor, I can take an x squared out of both terms, so I do. And that leaves me with x to the 4th minus 16 equals 0. Now, this is what I'm talking about. It would be really easy to say, oh, well, that's just going to be equal to 0 on its own anyway, and we make that disappear. Don't lose it. We need to hold on to that. We need to have that piece of the solution. Carrying on, we look at this piece in brackets. We notice that it's in itself is the difference of squares. So this can factor into x squared plus 4, and this becomes x squared minus 4. So that's as far as that goes. That's as far as that goes. That, though, is a difference of squares again, so it can factor one more time. X squared comes down, x squared plus 4 comes down, and then this factors into x plus 2 and x minus 2. Now that we've factored everything, we can go ahead and solve. So we need to solve for each of the pieces, just like we did in our first example. So if x squared is equal to 0, that means x is equal to 0. If x squared plus 4 is equal to 0, this implies that x squared is equal to negative 4. Can't take the square root of a negative number, so no real solutions. That, in my little scribbles, is just the word solution abbreviated with an apostrophe in there. Carrying on, we still have x plus 2 equal to 0, which implies x equal to negative 2. And then we have x minus 2 equal to 0, which implies x is equal to positive 2. So then we have three real solutions, x equal to 0, x equal to -2, and x equal to +2. So because there was a real solution on that, that was one of the reasons we needed to make sure we didn't divide out that x squared. Now, what does all of this start to look like in a graph again? Just because it's fun to be able to look at those things. So let's flip back to our Desmos for a minute. So the previous question that we just did was this one, the 3x squared plus 13x minus 10. Zoom out so you can see that your solutions, there's one, and then there's the other right at 2/3. So you can see that, again, just makes the parabola graph. And the bottom is way, way down there. This one, though, is a much more interesting graph. You haven't seen one that looks like this yet. It's got lots of dips and curves into it. But you can see, because it's got lots of dips and curves, we actually do cross the x-axis 3 times. One right at 0, we touch it before going back down again, and then at -2 and +2. So, lots of fun on graphs like that. This is, as you're working through your homework, a pretty good way to double check that you have done your factoring correctly and hit your solutions. It's just a nice visual way to confirm the mathematics that you've already done. Okay. Sometimes you come across questions that don't factor nicely. You get a quadratic equation, and it doesn't have anything that factors really nicely like this. So what do? Well, I get to introduce you now to a thing called the quadratic equation. The quadratic equation, I do provide it on the test, so you don't have to memorize it. You probably want it on your own reference sheet, though, with notes to make sure that you recognize how to use it. This is it. X equals -b plus or minus square root of b squared minus 4ac, all divided by 2a. B, A, and C are numbers from your quadratic equation. If you are given y equals, let's get this right now, ax squared plus bx plus c, these numbers, your coefficients and your constant from your quadratic equation, are the numbers that go into your slots A, B, and C. Okay? Now, this quadratic equation is really interesting. It does a whole bunch of stuff. The thing that I want you most to understand about it, though, is this part underneath the square root sign. The part underneath the square root sign is called the discriminant. So I'm just going to underline this right here. It's called the sure I spelled this right, discriminant, I-N-A-N-T. Big fancy word for the stuff under your radical. The discriminant can tell us things about our equation. If this area under the square root sign, if your b squared minus 4ac is less than 0, okay, which is to say it's a negative number, no solutions. Simply because we can't take the square root of a negative number. If your b squared minus 4ac is equal to 0, then we end up with only one solution. We just end up touching that x-axis once. That dip in our parabola just kind of touches it like that, once like that, right there, so just one solution. And then finally, if our b squared minus 4ac is greater than 0, then we're going to have two solutions. And they will both be real, two real solutions. Okay? This is sort of helpful because when you go to do this, instead of actually having to do out all of the calculations, if you suddenly notice that your b squared minus 4ac is going to be less than 0, you can stop. You don't have to do any more arithmetic. You don't have to do any more solving because you know you're not going to find any solutions. If, however, it's equal to 0, you'll know that you're only going to find one number out of this whole thing. If it's greater than 0, then you know that you have to do the whole thing out and you'll find two solutions. Let's take a look at an example. It's always easier to understand what I'm babbling on about if we can look at real numbers. So, I'm going to leave all of this here to start the example, and then I'm going to clean it up for a minute. And the reason is I want to do this. We're being given, for our example, of the following equation. 5x squared minus 2x equals 10. Step 1, of course, says rearrange, so we do that, and we find that we have 5x squared minus 2x. Make sure you get your signs right. 10 is coming across the equal sign, so it becomes minus 10 equals 0. 5, negative 2, negative 10. These now correspond to A, B, and C. And are going to go into our equation. Okay, so I just wanted you to see all that while I still had the this written out, so you can see there's your A, there's your B, there's your C. We're going to put them into this quadratic equation. Okay, I'm going to do that again. I'm going to clean this up. I just wanted everybody to be able to see that all on one whiteboard all at once. So I'm going to leave the quadratic equation up just for a minute so you can see that this is all going to go in there. We ended up with 5x squared minus 2x minus 10 equals 0. There's my A, my B, and my C. I'm going to write it out for clarity. A equals 5. B equals negative 2. And C equals negative 10. I will put these into the equation. My negative of B is now a positive 2. The negative of a negative becomes positive. Plus or minus the square root of negative 2 squared minus 4 times 5 times negative 10. And then this whole thing will be divided by 2 times 5. So this generally takes up a fair amount of paper. I'm going to try and squeeze it in here, but I may need to clear the board a couple of times so you can see it. We'll see how it goes. The 2 continues to come for the ride. Plus or minus square root of negative 2 squared is 4. Negative 4 times 5 is negative 20. Negative 20 times negative 10 is positive 200. So I'm going to get 4 plus 200. 4 plus 200 is going to be 204, which is going to be a positive. So we are going to get a number greater than 0, which means we are going to come out with two solutions. 2 times 5 gets me 10. We do this again. 200 plus or minus the square root of 204. All divided by 10. When I do this, my recollection is I can only take out the square root of 4 from this. So I end up at 2 plus or minus 2 square root 51 divided by 10. Oh, and I'm just barely going to make this in here. 2 will divide 2, will divide 2, will divide 10. So I end up with 1 plus or minus square root 51 divided by 5. So hold on to that number for a minute. I'll give everybody a chance to make sure their notes are up to date, or up to this point, and then I'm going to bring this up and I'll show you what we do with that. Oh, and I have had people asking me questions. Yes, so the numbers are absolutely corresponding to the numbers pasted to the x's. The 51 came from, sorry, this was just a quick bit of math I did in my head. 204 is equal to 4 times 51. I took the square root of 4 to get the 2, and the 51 stayed under the square root side. Okay, so I'm going to just put this up here for a second. 1 plus or minus square root of 51 all over 5. So now that we have that, we actually have to do that. So what I mean by do that is I'm going to need 1 plus the square root of 51 divided by 5. Or I'm going to need 1 minus the square root of 51 divided by 5. Now when we do that, we're largely looking for calculator approximations. Our first one, sorry, I thought I had this up, but I erased it on myself. This one, we end up as, once you plug this into your calculator, approximately 1.628, and that's approximate. Going the other way, what I mean by going the other way is when we do the minus, we have x is equal to negative 1.228, approximately. So there we go. 2 real solutions. They're not really nice numbers. If they were going to come out as really nice numbers, we could have factored it using our normal methods. But that's why we have the quadratic equation for times when things don't factor nicely. Now, we'll take a look, make sure we've done our calculations correctly. Just pop over to our handy-dandy graphing calculator. Oh, I haven't put this one in here. Well, let's plug this one in here really quickly. 5x squared minus 2x minus 10. There it is. Yeah, negative 2.28 and 1.628. So there we go. Those are those 2 little points, exactly where we expected to find them. This takes a little bit of practice, largely because of the positives and negatives, and then practicing with the calculator. So don't be afraid to practice this a couple of times just to make sure that everything is coming out correctly for yourself. Okay, moving on to solving inequalities. We started taking a look at inequalities when we were graphing. And we were mostly graphing straight line inequalities, linear inequalities. Now we're going to take a look at what happens when we have x squareds thrown into the whole mix. So, solving inequalities. Solving inequalities is not too different from what we've been doing before. There's just some extra steps added. Because they are inequalities, there's whole regions that we need to identify. The same way when we were graphing our lines, and we would find the line, boom, then we'd find a test point, usually 0, 0, and find out which side, the good side or the bad side, the side that we want or the side that we didn't, and we'd shade in the side that we want. That's what we were doing with lines. We're going to do the same thing with these quadratic inequalities, but there are a few more regions, so it just takes a little bit more work. So, for example, if we are given x squared minus x greater than or equal to 12, I'm going to start by, again, same steps as before. Step 1, rearrange. Okay, that 12 comes over and I end up with x squared minus x minus 12 will be greater than or equal to 0. Next, we're going to take the related equation. And by related equation, I mean instead of taking the greater than or equals to part, we're just going to take the equals to part. So you can call that step 1a. Nothing's really changed, but 1a is the related equation, which gets us x squared minus x minus 12 equals 0. Then we can move on to the customary step 2, which is factor. What multiplies to make negative 12 but adds to make negative 1. And we end up with x minus 4 and x plus 3 equal to 0. From that, we can find solutions. Okay, in this case, we can jump to it. X equals 4 or x equals negative 3. Now we're going to move on to the part that's slightly different because we're dealing with inequalities. So this is step 4 now. Test regions. What do I mean by test regions? That's a little blurry. Let me see if I can just move that into focus. There we go. So step 4, testing regions. What do I mean by regions? Well, if we put this out on a number line here just for a moment, and we've got one point right there at 4. We've got another point down here at negative 3. There's 3 places here that we can be looking at. We can be looking at this area down here, which is everything that's less than negative 3. We can be looking at this area up here, which is everything that is greater than 4. And we can look at the area in between. What's between negative 3 and 4? So we have 3 regions, really, that we're looking at. And the reason that we want to be looking at that is because we can, when we go back to our original equation, because it's looking for what is greater than 0, what it's essentially saying here, we want to, or what we're essentially trying to find out, is where in these regions are we actually going to be greater than 0? Okay. So we'll test what happens if we need an x that is going to be less than negative 3. We need an x value that is between negative 3 and 4. And we need an x value that is greater than 4. So for the x value that's less than negative 3, I'm just going to go with negative 4. For a number between negative 3 and 4, I like to go with 0 whenever I can because it makes life easy. So we'll test 0. And for x that's going to be greater than 4, we can just go with x equal to 5. So these are the numbers that we're going to use to test our regions. So just to be clear, this one down here is going to be the x equals negative 4. This region in here will be our x equals 0 test, and this region over here is our x equals 5 area. How do we test that? We're going to actually put these numbers back into our equation. So we'll start with the negative 4. Negative 4 squared minus negative 4 minus 12 is what we're trying to find out. Is that going to be greater than or equal to 0? Well, negative 4 squared is 16. The negative of negative 4 is plus 4, and then minus 12. 16 plus 4 is 20. 20 minus 12 is 8. Is 8 greater than or equal to 0? We can say yes. So with negative 4, this gets a green. Yes, that's part of the region that we're looking for. We're going to do it again 2 times, once with 0, once with 5. I'm not even going to move any of this. I'm just now going to go ahead and put the 0 in here. And when we do that, 0 squared is 0 and 0, so the whole thing just ends up as negative 12. Is negative 12 greater than 0? The answer there is no. So we can say it's not going to be in the in-between area. And then finally, we'll do it one more time, but this time I'll do it with 5. Negative 5 squared, or 5 squared is 25, minus 5 minus 12, so negative 25 minus 5 is 20, minus 12 is still going to be 8, which means that once again we have a yes. So then our regions that we actually want to have are going to be this x greater than negative 3, or less than negative 3 rather, and x greater than negative 4. Those are going to be the areas that satisfy our equations. So our solutions, this is where we get to the part where we actually state our solution. Our solutions are going to be exactly that, x less than negative 3 or x greater than 4. Okay, let me catch up on a couple of questions. Caitlin, generally you only use it when you can't factor easily simply because it takes much more time. If you can factor things easily in your head, and it does factor easily, go ahead. If you look at it and you say, I'm sure this factors, I just don't want to go through the work of it, you can also use the quadratic equation to do that, and I often do, just to come up with trying to figure out what my solutions are relatively quickly. Melanie, yes, I was covering that right at the beginning of class. So we're doing tests this Thursday and also tests next Tuesday and next Thursday. I'm also available for questions on both of those days. If you're not there for tests or questions, you are not required to come to any of those days. Does that answer the question clearly? No problem. Awesome. Okay, so all of this that we've just covered off on all of this solving inequalities, let's take a look at that on the graph, because sometimes this all makes just a little bit more sense if you can see it visually. So let's take a look at this on the Desmos. So this is the equation right here. And as you can see, immediately we're not going to see the whole graph because the vertex is way down below. And because it's an inequality, it doesn't really matter. It's showing us what we need to know in terms of the solutions. What we're looking for is in this area that's less than -3 and this area that's greater than 4. A couple of small points that I want to point out because they, as you move forward in your higher mathematics, these are the little half points that can catch you up. Note that this is a solid line right here. The reason it's a solid line is because we're saying less than or equal to. If I were to switch this equation from this version down to, I thought I had a different version of it, but I don't. But I'm just going to grab this equation just for a minute. You can see that this one's got some dotted lines on it. The reason it's got dotted lines on it is because it doesn't have the equals. So what this is implying by using the dotted line is that you're not actually using those numbers. You're just getting really, really close to those numbers. Okay, so that was one of the things that I wanted to show you. I also wanted to show you, using this exact same equation, this was the one that we just solved, x squared minus x minus 12, and it shades the outside, below -3, above +4. If we had switched the inequality sign on that, it would shade the part in the middle. It would actually just switch the shading. We would only want that one region between -3 and 4. So that's why we do the testing, is because that's what's going to happen. I think I pulled up another example in case we want to do one later if people need to see this again, so I've got that example ready for later. Okay. Sorry, just before I flip out of here, does anybody have any questions or things they want me to just highlight while I've got these up on the Desmos? Okay. We will come back to all of this when we're doing the question sections of the lecture. So that is doing your inequalities. It's the same as doing your other stuff, just with extra steps. Moving on to now the last topic of the course, systems of linear equations. Now, when we talk about a system of linear equations, all we're talking about is more than one line at a time. So if I say a system of linear equations, all it means is more than one line. That's all. More than one line. Really fancy way of saying that. Now, when we find a solution to a system of linear equations, this is where the lines cross. Okay. In our previous solutions so far today, the line that we've been crossing has been that x-axis. Now we're going to look for places where we have two independent lines that cross. Okay, so where that line crosses, this means you're going to get a coordinate pair. For those of you going, I know what that is. What is he talking about? This is your x-y pairing of numbers, so you can see it on a graph. Now, there are three common ways by which we go about solving systems of linear equations. One of them is by graphing. One of them is by substitution. And then the third version is elimination. Graphing is fairly straightforward. You've got two lines, you put them on a graph. Line number 1 goes like that. Line number 2 goes like that. Solution is right there, right where they cross. I will show the graphical solutions to a couple of the examples that we go through as we go through them. I'm not going to try and do this out separately. It really is as straightforward as it sounds. Moving on to substitution. Oh, which one do I have first? Sorry, I have elimination first. We're going to start by doing a process of elimination. So, from an example, we're going to solve by elimination. Our example says we have a store that sells 2 types of flowers, yellow and which have 2 leaves, and red flowers which have 3 leaves. So 2 types of flowers. Yellow, which I'm just going to mark with a Y. They have 2 leaves. And then red flowers, which I'll mark by an R, and they have 3 leaves. There are a total of 154 flowers in the store, and a total of 411 leaves. So 154 flowers, 411 leaves. How many flowers are red and how many are yellow? So some of the hardest parts about stuff like this is how do we set this up? We have 2 types of flowers. There are 154 flowers in total. We've said that our flowers are Y and R. So the first thing we can say is that Y plus R has to equal 154. Okay, that one's fairly straightforward. How many flowers have we got? Well, some yellows, some reds, add them together, we get to 154. No problem. Now, the 411 leaves, each of our yellow flowers has 2 leaves, so we can say that there are going to be 2 leaves on each of our yellow flowers. And then there are 3 leaves for each of our red flowers, so 2 times Y plus 3 times R will give us 411 flowers. Now, in order to solve this by elimination, what we're actually going to do is we take a moment and we add or subtract, depending on what we need to do, our 2 equations. And when we do that, we want to make sure that at least one of our variables disappears. In order to make that variable disappear, I'm going to choose one. In this case, I'm going to choose the Y. I'm going to make our Y disappear. In order to make that Y disappear, I'm actually going to take this whole equation and I'm going to multiply it by 2. And when I do that, I'm going to get 2y plus 2r equals 308. And then my other equation stays as it is, 2y plus 3r equals 411. Now I'm going to subtract these equations. When I subtract these equations, I end up with 0 y's. I end up with negative 1 r's, and then I end up with negative 103. Well, negative r equal negative 103. This means that r is equal to a positive 103. If r is equal to 103, well, then it's really easy. I then know that y plus 103 will equal 154. I subtract 103 from both sides, and y is equal to 51. That should be a 5, not a 6. And those are our solutions right there. We have 103 red flowers and 51 yellow flowers. So to go through those steps again, set out your equations. Once you have your equations set out, identify the variable you want to get rid of. Multiply the appropriate equation in order to make sure that you can get rid of that variable when you add or subtract. Do that addition and subtraction to solve for one of your variables. Once you've solved for that variable, put it back into your original equation and solve for the other variable. So now what we know is that if we were to plot this on a graph, with these being the x and the y coordinates, we would have the point 51, 103. That would be exactly where we cross those lines. Okay, if elimination isn't your cup of tea, there are other options. You can always solve by substitution. Oh, wait, there's a question here. Why did the 2r and the 3r become a negative? I subtracted. So I had positive 2r minus positive 3r. So 2 minus 3 gets me to negative 1. Does that make sense? 2 minus 3 gets me negative 1. Cool. Okay, good. Glad I caught that before I erased it. Moving on to substitution. Substitution is just what it sounds like. We are going to substitute one term for another. Substitution. I think I spelled that right. Okay. So, for example, say that we are given the following system of equations. We're being told that 3x plus 2y is equal to 5, and then we're also being told that x minus 3y equals 7. As opposed to what we were doing before, where we manipulate one of the equations to match the variables in the other equation, all I'm going to do in this case is I want to get one letter all by itself. The easiest letter to get by itself is going to be this x. All I have to do is move this negative 3y to the other side of the equal sign. And when I do that, we discover that x is equal to 7 plus 3y. So this is now what x is equal to. So I'm going to do that in a different color just for a quick moment. Because x is equal to this, I can actually put this into the other equation in place of x. And when I do that, I end up with this thing. Oops, let's go with the right color bracket. So it's the same as the first equation, except now I have replaced the x with what I found x is equal to. And when I do that, I now have the entire thing just in terms of one variable. Now that it is just in terms of one variable, we can solve it. We know how to go about doing this. So we start by sharing. 3 times 7, 21. 3 times 3y, 9y. And then the 2y comes with it. 9y plus 2y gets me 11y. No problem. We're going to subtract 21 from both sides. Which gets us down to negative 16. I'm going to divide by 11 on both sides. And that leaves us with a final answer of y equal to negative 16 over 11. Not a particularly pretty number, but it's a number, and we can work with it. So now that I have a solution for y, I'm going to take this and I'm going to put it back into one of my original equations. I'm going to put it back into this equation just because it looks like it's going to be easier to solve. So the second half of this then is that this then goes back into the equation. So in order, that looks like, just the space again, I'm going to get x minus 3 times negative 16 over 11. Sorry. What am I doing here? Oh, I'm going to use this version. That's what I did in the notes. Instead of putting it into this equation, sorry, I put it into the equation where I already had x all by itself. That makes more sense. Goes in there. So then, let's try writing this out again. X equals 7 plus 3 times negative 16 over 11. We're going to have to do everything over 11 because we have to add fractions. So 7, when I put it over 11, is actually going to be 77 over 11. 3 times negative 16 is negative 48 over 11. So now I have 77 minus 48, which is simply 29 over 11. So this means that my solution is going to be the coordinate pair 29 over 11, negative 16 over 11. And if we were to graph these points, that's where we, or graph these lines rather, we would see that that's exactly where they cross. Taking a moment, we'll actually do that. Let's take a look at the graphing calculator. So there was one of our lines, 3x plus 2y equals 5. It's in black right there. And then our other line, x minus 3y equals 7. And where do they cross? Right down there. 29 over 11, which is 2.636 approximately, and negative 16 over 11, which if you plug it into your calculator, you'll find is negative 1.455, et cetera, et cetera, et cetera. So there is the graphical solution to our substitution. Okay, just before we take our quick 5-minute break, there's just a couple of little things that I need to go over in this whole world of systems of equations, and that is the special cases. There are 2 special cases we need to look at. We've talked about them in another form, but they'll make a little bit more sense here. So let's take example, special cases. Sorry, let's change the title on this. Special cases. Example number 1. If, let's say we have the following system of equations, 2x plus y equals 7, and then 4x plus 2y equals 10. From this first equation, I can rearrange this so that y is equal to 7 minus 2x. And then I'm going to use this, I'm going to put it back into my second equation, and we'll get a solution, we hope. So 4x plus 2 times 7 minus 2x equals 10. We share the 2, and we have 4x plus 14 minus 4x equals 10. My 4x's cancel, 4x and minus 4x, and I'm left with the statement 14 equals 10. That's not true. That's a lie, mathematically speaking. When this happens, you haven't done it wrong. Okay? We just need to recognize what that means. It means that there is no solution. What happens, or when do we get no solution between two lines? The other way you can think of it is two lines that never ever touch. Well, two lines that never touch we simply know those as parallel lines. Okay. So that's special case number 1, parallel lines. If you arrive at a contradiction, you have parallel lines. So that's special case number 1. Special case number 2. Again, let's say that we've got a system of equations, but this time it says 2x plus y equals 7, and my second line is now 4x plus 2y equals 14. Same rearrangement. Y is still going to equal 7 minus 2x. Putting it back in, now I'll get 4x plus 2 times, not y minus 7 minus 2x equals 14. We do the multiplying out. 4x plus 14 minus 4x equals 14. My 4x's cancel, and I'm left with the statement 14 equals 14. Well, that's absolutely true, but not particularly helpful until we start to recognize what this means. This means that I can use all real numbers as my solution. Why can I use all real numbers? Because it doesn't matter what pair of numbers I pick, it's always going to work out that these things are overlapping. What kind of lines overlap all the time? The same line. Really, this is just the same line written out in a different way. So if you picture it, if I've got a line that's doing that, and then I have another line right on top of it the whole way, it doesn't matter what numbers I pick, it's going to be the same line the whole way through. Okay, and with that, I have come to the end of the lecture portion. I have now talked about absolutely everything you guys need to know, at least until you get to your next math class. Let's take a 5-minute break. We'll come back at 5:46, and I will happily take questions that anybody might have on this or anything previously in the course. Okay, everybody, we're back. I have some requests for questions. Before I go on to the polynomials homework, let me address Jackie's question first. I'm going to do it visually. In the special cases, could I explain again why this contradiction of 14 equal to 10? Let's take a look at it on the graphing calculator just for a quick moment. So the original pair of equations that we were given were 2x plus y equals 7. And there it is in the green line right there. And then the other one was 4x plus 2y equals 10. And we came up with the statement 10 equals 14, which we know is not true. If we graph that, we can see that they're parallel. They simply won't line up. And anytime you come up with a true statement, like, or a false statement rather, like 10 equals 14, because 10 does not equal 14, we know it's not true. Therefore, the lines must never touch. Therefore, they're parallel. The other one, the non-contradiction, where we had 4x plus 2y equals 14, well, you can see, as I toggle this line on and off, it's the exact same line. They just overlap everywhere. And of course, this other line doesn't touch either of those lines. Does that help? Does that make it a little bit more clear? Okay. Taking a look at the polynomials homework, I have a number of questions. We're starting with question 4. This is where we're looking at rationalizing the denominator. Hold on a second, I seem to have actually just misplaced my pen. How bizarre. Okay, it will show up or it won't. So question 4C. This is from the polynomials homework. Question 4C gives us 5 over root x plus 5. So this is the situation where we want to deal with the conjugate, which is to say we need to flip the sign on our thing on the bottom. So we're going to multiply this by root x minus 5 over root x minus 5. 5 times root x is, of course, just going to be 5 root x. 5 times negative 5 is negative 25. On the bottom, when we do this out, root x times root x gives me an x. I get negative 5 root x and positive 5 root x, so those cancel out. And then positive 5 times negative 5, negative 25. Then we take a look to see if there's anything that can simplify here. The answer is no. If I want to, I could factor this top one just so that we can see it. And it gives us a 5 times x minus 5, which is, of course, where we came from. But we're looking to see if we can get rid of anything. The problem is I don't have a 5 on my x term, so really we're done there. Yes, Diane, I can. I will add that to the list. Okay, going on to 4E. Sorry, which part positive?
5 over the root of x plus 5. Why not times it positive? Why did you switch it to negative?
We do it to negative because we're trying to make the terms that would come up in the middle disappear so that we don't end up with any radical signs. Our whole purpose is to get rid of that radical sign, right? So,
right, but don't we set it in an example? Don't we times it by a positive?
we always multiply it by the opposite sign. Okay, so if I have positive in the first bracket, which I do here, then I need negative in the second bracket. If I'd been given negative in the first bracket, then I would want positive in the second bracket.
When you do negative root of x, then too?
No, you just change the sign in the middle. Always just have opposite signs in the middle.
Okay, just for numbers, but not for roots of other things.
Yeah, it's just that sign in the middle. You just want to make sure that whatever's happening between them. So if I'm understanding your question correctly, you're asking like if we had negative root x minus 3, well then we would have to multiply that by negative root x plus 3.
Yeah.
Yeah.
Okay.
Okay, so it's just that sign that changes.
Okay.
Okay?
Yeah.
And when you do that, each and every time, it gets rid of that radical.
Okay.
Okay?
Mm-hmm. And that was the part that confused me, was the negative positive. I had no idea what was coming and where.
Yeah, and so, and the whole idea, if you're not sure, you can multiply them out. So when I multiply this out, the negative times negative, of course, is going to cancel. Radical x times radical x is just going to leave me with the x. Negative root x times 3 will give me negative 3 root x. Negative 3 times negative root x is then going to give me the positive 3 root x, and they'll still cancel out. Negative 3 times negative 3 for negative 9, and those will disappear.
I get it now. This makes sense. Okay, thank you so much.
You're very welcome. Do you still want me to go through E and F on these?
Yeah, I think there were different reasons why I got them wrong.
Okay, let me run through them. Okay, E says root 2 over 5 minus root 10. So, again, just that sign in the middle is what changes, so this is going to be 5 plus root 10 over 5 plus root 10. And when we do that, I end up with 5 root 2 plus root 20, which we'll have to clean up in a second. And then on the bottom, 5 times 5 gets me 25. Positive 5 root 10, negative 5 root 10, they cancel. Root 10 times root 10 is 10. This needs to clean up a little bit. The bottom is the easiest place to start. 25 minus 10 just leaves me with 15. On top, I have 5 root 2. The 20, I can take out a square root of 4, which is 2, and it leaves me with a root 5. That's really not clear. Let's try that again. 5 root 2 and 2 root 5 all over 15. There's nothing in common all the way around, so that's our final answer. I'm going to keep moving. I'm watching time. I don't want to go too over today. Skipping back up to the top, we'll do 4F really quickly now. Root 3 over root 12 plus root x. Again, the sign in the middle changes, so we are going to be multiplying by root 12 minus root x over root 12 minus root x. And when we do that, 3 times 12 gives me root 36 minus root 3x. Nothing we can do about that one. Root 12 times root 12 is 12. The middles cancel. Minus x times x is x. To our last little bit of cleanup, I can take the square root of 36, which gives me 6. Nothing I can do here, so that stays as it is. Nothing I can do with those, so we're done there too. Cool. Lauren, I know that you're asking about the long division. I'm going to come back to the long division. I'm just cognizant that those tend to take a little bit of time, so I'm going to skip ahead. I'm going to do the graphing question that Diane's asked about, and then I'm going to go back and do the long division questions. So, we're looking at question 15 from the graphing homework. So we're graphing inequalities. This is good. This picks up on a little bit of what we were doing today. So this is graphing. And we'll start with 15a, which is giving us 3x plus 2y less than or equal to 6. Really wish I could find my black pen. Very strange. Okay, I'll do a graph in grid then. So, we're going to start by doing this by the intercepts, okay, which is the easiest thing to find. And we'll find the intercepts for the related line, 3x plus 2y equals 6 is what we'll start with. So if I put in 0 for x, it means that 2y equals 6, y equals 3, so we have the point 3, 0. If I put in 0 for y, that means 3x equals 6, so x is equal to 2. Sorry, that one was backwards. 0, 3, that's better, and then 2, 0. I put these on my graph. The point 0, 3, 0, 1, 2, 3 is there, and then the point 2, 0, 1, 2 is there. Let's try that again and see if I can actually make the dots connect. Close enough. Okay. So now we've done the easy part, which is the actual finding of the line. But we don't want this line. We want this inequality. So we need to test a point, and I'm going to test the point 0, 0. And I'll just, you know what, just for clarity, I'll put test point in a different color. We're going to test the point 0, 0. Well, the 0, 0 point is right there. If I put 0 in for both of these things, then I'm going to get 0 plus 0 less than or equal to 6. Is 0 less than or equal to 6? The answer there is yes. So then the 0, 0 point is on the side of the line that I want. And so I shade in that side. And then for clarity, we should have labels on our points. So we should have this as the point 0, 3. We should have this as the point 2, 0. And we should label the point 0, 0 for our test point also. Does that help? Is that clear how we got all of that? So the shading. The line that we're trying to deal with, or the equation that we're trying to deal with, is this 3x plus 2y less than or equal to 6. So we're trying to find the side where when we pick an x and a y value, it's always going to be less than or equal to 6. It's going to be on one side or other of this line. I pick a point at random. I tend to pick the point 0, 0 whenever I can, just because it makes my life really, really easy, because it turns one side of my equation entirely to 0. Is 0 less than 6? Well, 0 is less than 6. Because it is less than 6, because it makes this statement true, that's the side of the line I want to shade. Because I know that no matter what pair of points I pick from this side of the line, when I put those values into this equation, the equation will still be true. Great. Okay, I'm watching the time. I want to try and get in at least one of these long division questions. And then there are 2 other questions after that, so I'm going to keep moving. Do you want me to do one more graphing, though, before I move on? Okay, so I'm going to move on. Let me take a look at which one I want to do. Let's do C. We'll do 15C. Okay, 15C says 5x plus y greater than or equal to 2. Again, I'll start by finding my intercept points for the related line 5x plus y equal to 2. I put 0 in for x, y is equal to 2, so that's the point 0, 2, easy. I put 0 in for y, and then 5x is equal to 2. X is equal to 2 over 5, so then we're at the point 2 over 5, 0. 2 over 5 is like 0.4. It's a little less than half. Draw out our graph, x, y. We do our points. I need the point 0, 2. It's there. I will mark it as 0, 2. I need the point 2/5, 0. Well, for our purposes, it's just about a half, so I'm just going to put it there. I'll go with 2/5, 0. My line is going to go right through there, but you can see that it's labeled. And I go like that, and that's close enough for what we need to do. We have 2 distinct sides. My 0, 0 is not quite as clearly where I necessarily want it to be. I'm going to move just a little farther out, and I'm in fact going to use the point, just for clarity in this case, -1, -1. Okay? Because again, I can clearly see that it's on this side of the line. So I put these numbers in for my x and y in here. So I will get 5 times -1 plus -1. And I need to know, is that going to be greater than or equal to 2? 5 times -1 is -5 minus 1 gets me -6. Is -6 greater than or equal to 2? The answer is no. So that is not the side I want. I want, if that's my test point there, I need this side. Okay. If you have more questions on this, I'm also happy to take this up on Thursday if you're either before or after you've written the test. Either or. Going back to long division for a second. So back to the polynomials homework. I'm looking at question 5a to start with. So again, from polynomials, question 5a. Says I want x squared minus 6x plus 3 divided by x minus 1. So then we set this up, and it looks like this. X minus 1 goes into x squared minus 6x plus 3. And I start by asking myself, what can I multiply x by to turn it into an x squared? And in this case, the answer is going to be x. X times x gets me x squared. X times negative 1 gets me negative 1x. We subtract. That goes to 0. We've designed it that way. That's good. Watch our negatives and positives here. Negative 6x minus negative 1x is the same as saying negative 6 plus 1. So we actually end up just at negative 5x. Or bring down the 3. What do I multiply x by to turn it into negative 5x? I multiply it by negative 5. Negative 5 times x, negative 5x. Negative 5 times negative 1, positive 5. Then we subtract. First part goes to 0 because we've designed it that way. 3 minus 5 gets us negative 2. So then our remainder becomes negative 2 over x minus 1. Why am I not timesing everything by x plus 1? Mostly because I don't have a radical in the denominator. There's no reason to change this denominator. And if I multiply everything by x plus 1, it won't change that I still ultimately have to go through this process. What we're trying to do in a strange sort of way is we're trying to force factor this first equation. We're trying to find out how many times can I stick this x minus 1 into this equation. And one of the things that we can do, and I haven't talked about this much because you don't often need to do it, but you can double check yourself. I can take this x minus 1 and I can take this final answer, x minus 5 plus negative 2 over x minus 1. And if I multiply them together, I should get x squared minus 6x plus 3 back out. So if I go like this, let's make sure I'm going to have enough room for this. Take this up just a little bit and go into a different color so it doesn't get too confusing here. If I take x minus 1 and I multiply it by x minus 5 minus 2 over x minus 1, and then I multiply this out, this is going to come back. Yes, 3 minus 5. Gets me to negative 2. And it is sort of reverse engineering the question. So, x times x, x squared, x times negative 5, negative 5x. X times this whole fraction becomes negative 2x over x minus 1. I'm going to see if I can stretch this out here. I'm going to bring this down just for a little bit of room. X squared minus 5x minus 2x over x minus 1. Negative 1 times x is negative x. Negative 1 times negative 5 is positive 5. And then negative 1 times this just becomes 2. Positive 2 over x minus 1. I'm squeezing this in here, but it'll all work out. So, negative 5x plus 5. We've got all of these pieces. Let's stick them in order. I get x squared minus 5x minus x is minus 6x plus 5. And then my things can come together, and I end up with negative 2x plus 2 over x minus 1. Now, this doesn't look like we're going to get there, but we actually do. If I factor a negative 2 out of both of these, let me just do a quick sidebar over here. Negative 2x plus 2, come over here, where there's room. Negative 2x plus 2 over x minus 1 can also be negative 2 times x minus 1 over x minus 1. So now those cancel, and I'm just left with that negative 2. X squared minus 6x plus 5 minus 2. Well, now my 5 minus 2 gets me that 3 back. And you can see through my random scribblings here that we get right back to where we started. So, yes, that's a long way around of saying, just like in long division, when you multiply those things together, you should get back to this one. Let me do B just for clarity. So, 5b says we want x to the 4th minus 3x plus 1 divided by x plus 2. So we need to rewrite this, and I end up with x plus 2 goes into x to the 4th. Now we have to watch this. I need 0 x cubed, and I need 0 x squareds minus 3x plus 1. If you forget those things, it often does not work out for you. So, how do I turn an x into an x to the 4th? We multiply it by x cubed. And when we do that, we get x to the 4th plus 2x cubed. We subtract. That goes to 0. That becomes negative 2x cubed. We bring down the 0x squared. What do I multiply x by to make it into a negative 2x cubed? We multiply it by negative 2x squared. That gets me negative 2x cubed by design. Negative 2x squared times 2 is negative 4x squared. We subtract. That goes to 0. That becomes positive 4x squared. We bring down the negative 3x. What do I multiply x by to turn it into 4x squared? I multiply it by 4x. That gets me 4x squared. 4x times 2 gets me positive 8x. We subtract. That goes to 0. This goes to negative 11x, and I bring down the 1. What do I multiply x by to turn it into negative 11x? I multiply it by negative 11, giving us negative 11x by design and negative 22. We subtract. That goes to 0. We end up with a 23. So we then say 23 over x plus 2. Yeah, it's almost always 9 times out of 10, if you find you're having problems with one of these long division questions, just go back and check those positives and negatives. Okay, I'm cognizant of the time, so I'm not going to do 5D at this point, but I am going to jump over to question 6D really quickly, and then hopefully we can get out 7D as well. So, 6D, under the polynomials homework, asks, we're trying to factor out common factors, and this one is giving us 6a times a plus 1 plus 18 times a plus 1. So there's a bunch of stuff that we can do here. A bunch. That's an exaggeration. There are a couple of things we can do here. The first thing we want to recognize is this a plus 1 term is what's common to begin with in both of these terms. Like factoring by grouping, when you see it like that, you can factor it out. So a plus 1 becomes the first term that we factor out, and that leaves us with 6a plus 18. A plus 1 is going to keep coming for the ride just for a second. I'm just going to move it in for a moment. Looking at 6a and 18, I recognize that I can pull a 6 out of both of those. They both divide by 6. So I'm going to factor out that 6, and when I do that, I'm going to be left with a plus 3. That's an a. And now I'm fully factored. Going to do the same idea, just one step earlier for 7D. Just get this written down. 3x to the 5th plus 3x to the 4th plus 6x cubed plus 2x squared plus 2x plus 4. Oh, yeah, no, you don't want to do that. I mean, if you do that, you should still ultimately get back to this point. But it's easier if you just recognize and can spot that that's a term that can be factored out first. Okay, factoring by grouping. It's specifically asking us to factor by grouping, so you can go ahead and assume that you group it in groups of 2. What can I pull out of, just for clarity then, that means that I'm going to group those together, I'm going to group those together, and I'm going to group those together. What can I pull out of those? I can pull out a 3x to the 4th. And when I do that, it leaves me with an x plus 1. Out of this, I can pull out 2x squared from both terms. And when I do that, it leaves me with an x plus 1. And out of both of these, I can pull out a 2. And again, it leaves me with an x plus 1. So now I'm in a situation just like I was for 6D, where I've got common terms. Now I've got 3 of them, but nothing's actually any different. There's still a common term, so I can pull it out of all 3 terms. And because I've pulled it out of all 3 terms, my second set of brackets has all 3 terms. Oh, it is. And this is clearly where I made some mistakes in putting this question together. That is a 3x plus 1. Which means the final answer. Good catch. I can pull a common factor out of these 2 things, which leaves me the 3x to the 4th plus 2, and then this actually just sits on its own. Like that. Oh dear, I made a mistake in putting that question together. Nice catch on that. What did I do in the answer key? Is that what's going on there? Oh, I made a mash of that, didn't I? So, for the record, ignore the answer key's answer for this question. I didn't construct the question the way I thought I did, so that's just a bad question at this point. My apologies for that. I will make a note to get that fixed. Okay, thank you for bringing that to my attention. I will correct the answer key and future classes will not have that same issue. Okay, so that's the end of class for today. Thursday is a test day and questions. Feel free to bring your questions. Please let me know in advance if you're planning on taking a test and which test you're planning on taking. Class will start on time and end on time. Thank you all very much. We'll see you on Thursday.